Hey there guys, let's go ahead and get started. Welcome to this Xamarin University webinar. I'm Jason DeBoever. I'm going to be your host for the next hour or so while we talk about machine learning. And more specifically, machine learning using Azure Machine Learning Studio. So first off, we're actually going to just do a gentle introduction into how machine learning works, what it is, and then we'll transition over to Machine Learning Studio. Before all that though, I, as I said, am Jason DeBoever, and I am going to be your host for the next little while. There's my Twitter handle and my GitHub right there, so you can go ahead and follow me. By the way, I am part of Xamarin University, and of course, we do offer a lot more than just these little webinars here. So every single day, we're giving live classes. We also offer one-on-one sessions, so you can actually talk one-on-one with me about your mobile issue, your Xamarin issue, or Android, iOS issues. We also do have self-guided learning. This means you can take your time, go through the materials, test out, and see how things went for some particular courses. Everything is subscription-based. We have a lot of flexible options and even a lot of free material out there, and everything goes from beginner to advanced. And of course, finally, you can use Xamarin University to get certified. Xamarin University itself is just part of Xamarin and part of Microsoft, along with the other tools like Azure, which we'll of course be spending a lot of time with today. You really can build a complete end-to-end solution. We can do things with iOS and Android, and we have a quite end-to-end mobile solution to offer. So obviously check out everything we have. What I'm talking about today, machine learning, is something that can help enhance your mobile application, of course, but it can also help enhance really everything else that you're going to do in terms of application development too. But a lot of our Xamarin stuff and a lot of our Microsoft mobile solutions are actually really geared very specifically towards mobile. So we have something for everyone. Please check out all that good stuff as well. Now on to today's session. So today, of course, as I mentioned, we're going to start with an introduction to machine learning. Just kind of tell you what it's all about. We'll take a quick look at Microsoft Cognitive Services, which leverages machine learning. We'll talk a little bit more about our machine learning introduction, our gentle intro to machine learning there. Finally, we'll dig into Azure ML Studio and then end on Q&As, all right? So, by the way, we're going to end on a Q&A, but anytime throughout this session, if you guys have questions, please feel free to use the chat window in order to ask questions. We've got people standing by. We've got other Xamarin University instructors hanging out there answering questions as you have them. Now, without further ado, let's get started on our machine learning talk. Now, by the way, guys, I'm not a statistician or machine learning expert. I'm not a data scientist. I am a software engineer. Now, I've spent some time digging into machine learning and learning about it, but we're going to look at some resources later where I'm going to point you at some true experts who really are, PhD data scientists, PhD statisticians who are digging a lot deeper into trying to teach you really what all this stuff is about. I'm going to give you the perspective from a software engineer. That's what I do, and I think that's what most of you are, since this session was titled Machine Learning for Developers. That's really what I want to do, actually, because it turns out that a lot of the machine learning sessions that I see out there are either geared towards people who already have extreme mathematics and extreme statistics background, or on the other end of the spectrum, it's geared towards complete newbies. What I want to do is leverage what you guys already know as developers, as software engineers. I want to leverage that because there's a lot of overlap in machine learning, but they use slightly different terminology. They say things in just a slightly different way. Their jargon is a little different than our jargon as developers. So I want to kind of do a little bit of translation there and introduce things in a way that is going to be relatively accessible, pretty easy for very experienced developers. And then, of course, later on, you still need to, if you want to really get into this stuff, know a lot of crazy math. So that part you will still need to dive deeper with and all that. But we can really get started and really get productive right off the bat, especially with ML Studio, which takes a lot of the big cliff to climb to start with. It takes that out of the way, and then we just have kind of a gentle hill to climb. So the goal of machine learning overall, it's just to create code that can take educated guesses for us. Right? That's it. It's the goal of the machine learning part of our operation is to create code, create algorithms that will take guesses for us. So for instance, recognizing images, or recognizing, for instance, that image contains the number 4 or the digit 4, right? So sometimes what our machine learning is going to do is do things that we as humans could do, but that writing an algorithm for is really difficult, right? So imagine trying to write that number, or write the code that would actually recognize the number 4. You'd like do some edge detection there, and then try to say, okay, well, the contrast ratio between these pixels is sufficient to create an edge, and therefore I'll start looking for angles. Oh, but this one is different because the edges are shaped different, and oh, by the way, we actually got spaces there, so how do I even detect that that's a contiguous character? So the algorithm written by hand would be incredibly difficult. Now, on the other hand, machine learning can also be used to do things that we have a very hard time with as humans as well. For instance, predicting the weather. We stink at that. But given enough data, given millions of records of historical weather data and the conditions that surrounded it, right? Maybe barometric pressure, or the weather of the last few days, or the color of the sky, right? It turns out that crunching all that data, our machine learning algorithms can actually do a pretty decent job at predicting the weather. We've also got a whole bunch of pre-baked things that Microsoft has already created, actually with Azure Machine Learning. Microsoft has created these algorithms for us and then exposed them. So I actually want to take a look at some of those. We're going to just jump in here and see our cognitive services webpage. And so all of these are actually exposed as APIs. And I'm going to come down here, scroll down a little bit, and we're going to look at the vision one, because this is a nice, easy one to demo. So let's go over to our computer vision API here and just take a look. So now you can actually upload your own images if you want to really prove that the API is working here. But let's see, we're going to click on, say, this one and have Azure Cognitive Services process this image for us using its Vision API. This is the Analyze an Image Vision API here. And take a look. It says, all right, it's an outdoor city building. It's recognizing all of these things. In fact, it even gives us a caption. Notice this is all JSON. So this is the actual return from a web service that's ridiculously easy to use. You send the web service this stream of data. Boom, it outputs what caption you could use, some tags about the data. Let's scroll down a little bit more, see some other interesting things that we have. So this is the read text, so OCR API, and you can see that, let's see, we'll just pick another one here. And again, you can upload your own image if you really want to see it, really proving that it does the job. And I'll actually click to the JSON again, the actual output of the web service. So we can see that, it actually tells you where the text begins in this image using this bounding box coordinates. So very, very interesting stuff, and then you can process that to just get the actual output there. So what does Azure do in order, or cognitive services, what do these APIs do in order to get to this point? Well, what they've done is they've collected a lot of data. They collected a lot of data, and then they used machine learning techniques to process that data to start to figure out what is the text that are in these images, or what are the tags in these images. The way they did this, collect a ton of data where they already know the results. So they've collected other images, other data, millions of records where they already know that it says life is like, or they already know that it says a goal without, right? Where they already know the actual resulting data. Then what we do is we run it through these standard algorithms along with some, tweaking of parameters until when we feed more data in, it actually starts to recognize those words. Now, it sounds kind of like magic when I say it like that, doesn't it? It's not quite magic. And actually, over the next few minutes, you're going to see that it's really not quite as magic as it seems. It's actually just a matter of math and a lot of data. All right, let's get back to the slide deck here. So again, what we do is create this code that guesses, right? We have to create code that guesses. And in order to do that, we start with data. And then the next thing we're going to do is just try to guess at a best algorithm to try to figure out what is the right magic formula. And then we're going to see, how did our guess do? Of course, we can then try again, and we can try again and try again. Now, this slide right here is definitely way oversimplified, of course. And in fact, this actually starts to introduce one of the things that makes it hard to talk through machine learning concepts. There's nothing terribly complicated in the overall picture of how machine learning works. But there are a lot of redundant concepts in machine learning, and therefore it can be a little hard to just explain quickly what's going on. So in fact, when I say guess an algorithm and then check accuracy and try again, this try again loop, there's actually 2 try again loops that are really part of getting machine learning correct. And we'll look at those in a little bit more detail later. But the first loop is actually a machine loop. It's actually our software, our machine learning software, doing the job. And then the next loop is going to actually be human. We're going to actually have to loop, keep trying again. The other redundancy here is I've already said we're trying to create code that guesses, create code that makes predictions. Well, here we are saying we're going to guess at the code that guesses, right? We're going to take our best guess at the code that guesses. And of course, if we were just, as I said, going to create one algorithm, written by hand, trying to do like the edge detection stuff for the number 4, like I said, check contrast ratios and all that, and then try again and try again and try again, this would be near impossible. Now, I bet we've all actually, or at least a lot of us, have actually been involved in projects where we've tried to do something like this, tried to create some heuristics for say, determining if someone is a high risk customer of our client's bank, or trying to create a heuristic to determine if something is spam. We've probably all been involved in these projects where we're trying to create this soft logic, this fuzzy logic, and then we just keep guessing again, and maybe we don't even have a feedback loop to see if we were right? We're just kind of, that's good enough, right? Maybe for determining complexity of passwords, right? Things like that. Anything that involves fuzzy logic is maybe not great to try to hand code as an algorithm. But it turns out that, data follows patterns. So if we actually have a ton of historical data for what we're looking at, we actually have kind of a menu of pre-built algorithms, of well-known algorithms that can tell us what we can expect, right? And this goes back to kind of our look at cognitive services, right? When we feed it a bunch of image data, maybe an array of pixels and an array of, red, green, blue, right? When we feed it that image data and it gets the chance to look at millions of records, and then we tell it about that data. We tell it, hey, there's a city in there. Hey, there is a building in there. Or hey, there's a person in there. It starts to be able to recognize those patterns over time with the right algorithms, with the right extra data that we give it, or the right parameterization of that data that we give it. So what algorithms we choose from these well-known algorithms are, first of all, going to depend on what we want to predict. So we'll keep things a little bit simple for now, and we'll talk about some of the most common types, and we won't get into, okay, how am I going to actually create image recognition? Although, believe it or not, that's a little easier than you might expect in many regards. But let's say we're trying to look at scaling values, like, for instance, money or time, really anything that goes up in a linear fashion. So counts of any sort could be a scaling value type, could use any of our scaling type of algorithms. And this is actually what we're going to dive deep into today. So I'll talk a lot more about that as we go on. Other options are, for instance, categorization. So if I want to be able to look at a bunch of emails and determine that is spam or that isn't spam, then I'm going to use a different set of pre-built algorithms and then feed my data into it. Yet another type is clustering. Now, this gets into an interesting thing here because both scaling and categories, I can actually create these algorithms by feeding old data where I know the answer, where there's kind of one true answer. And that's called supervised learning. So you can almost think of the supervision as okay, after I've tried to guess using a guessing algorithm, I'm kind of supervising. I'm able to say, no, you're wrong, algorithm. So we know the answer, right? When I'm training that up, when I'm trying to guess my algorithm, And for instance, well, we'll actually get into this a little bit more when we look at some of this scaling stuff. But when I look at emails, I can look at an email and the email text and the sender and the time and all that stuff, and then I can have an algorithm guess, is that spam or not? Well, then I can have humans review that, and if it's spam, it gets marked as spam, and we can determine either the algorithm was on 99% of the time or it was off 99% of the time, right? So we can tell it absolutely you were right or absolutely you were wrong. Now, clusters is a little bit different because I can't really do that with clusters. Clustering data sometimes is obvious, but sometimes it's not so obvious. Let's imagine that we have the Milky Way galaxy, right, which is kind of spirally, right? We have those spiral arms in the Milky Way galaxy. Now, one clustering algorithm might say, oh, I want to take each of those spiral arms, and each arm, despite the fact that it, wiggles around in that spiral fashion, we could say, okay, that is a cluster. Another clustering algorithm might, for instance, take the Milky Way and divide it into quarters, or however many clusters we ask for. Just chop it right down the middle like cutting a pie. Both of those are equally valid depending on your data and your business needs and what you're trying to do with that data. So it really depends. There's no true or correct answer with clustering. So this comes under something we call unsupervised learning. Those are the two big categories in machine learning, would be supervised, these two, and unsupervised, this one and others. Okay, now, as I said, I really want to focus in on the scaling values type of predictions or guesses. And so to do that, what we're going to do is look at some data in Excel, just to kind of get a general idea of data and what I mean by data that scales with each other. Let's open up my Excel doc here, and you can see that what I want to do here is basically be able to predict housing prices. And right now we're doing it based on one and only one piece of information. Now, in a real machine learning problem, we might literally have hundreds or thousands of columns of data that are going to help us predict one other thing. So in this case, it's just one-to-one, right? So keeping it very, very simple for this first example. And we can see that, okay, I have 1,000 square foot, and that is going to be I've got some historical data here, right? So a 1,000 square foot house has $50,000. A 2,000 square foot house is $100,000. Some other 2,000 square foot house cost $120,000. And of course, in the real world, our data is not going to always scale perfectly. So you're going to have some 2,000 square foot houses that cost this much and some that cost this much. So it's not going to be all super clean and easy and perfect trend lines, right? So we've got this data, and what I'm going to do now is I'm going to actually add a scatter plot for this so we can visualize it. And let's go to Insert here, Scatter. All right, so we've got our scatter plot here, and we can see there's my 1,000 square foot house cost 50, my 2,000 cost 100, my other 2,000 was 120. So there's our data right there. And now let's add a trend line to this. And my trend line here basically shows it's a linear trend, and it says, all right, here's the basic, trend that we see in the data. This is actually exactly what we want to do with machine learning. And in particular, there's a algorithm that we're about to dive into, one of the simplest, called linear regression. It does exactly this. It looks at all the data and tries to find a trend line through the data. Now, of course, with this little amount of data, I could have easily drawn that line roughly myself, right? I could just look at the plots and go, okay, it goes about through here. Now, that's pretty easy with even if I had a lot of data, but I was only looking at one column to predict one other, I can visualize it and do that pretty easily. How about if I add one more piece of information? Well, now I have two pieces of information. By the way, we can now see that it was adding the extra bedroom here that allowed this particular house to be a little bit more expensive. Right now, again, we can add lots and lots and lots, hundreds of features. But even adding just this one more column, by the way, columns are features in the vernacular of machine learning. So the input columns, like square foot and bedroom, would be called features. The one that we're trying to guess is called the label. So we have features and label. All right, now this actually is something that that Excel has kind of a bit of a hard time with. We can't really do a 3D scatter plot in Excel, so I can't even do that with Excel. I can go ahead and do that with some other tooling. So let me actually pull that up. I've actually copied and pasted the data into this Plotly right here. You can see it's the same data, and now I have a 3D scatter plot. I can't draw a trend line in here, but what we can roughly see is that my data is what it's supposed to be. I have the along x-axis here, I have 1,000, 1,500, so my 2,000 square foot. I have, if I turn this, I have 2 items at the 2,000 square foot, and those have 2 and 3 bedrooms respectively. And if I turn this again, we can see that it does match the appropriate dollar amounts. So we can still chart with this much data, though it's already really difficult. I can still sort of see where my trend line would be if I turn the chart in just the right direction, but it's already getting really difficult. Now, start to imagine if I had hundreds of features. Now, there's no way I'm doing this by hand. There's no way I can figure this out. I mean, even with the one-dimensional over here, right, the trend line doesn't exactly go through these points, does it? It's like a little above because it was kind of pulled by this one, because this one is a relevant data point too. So already things are not quite so intuitive with just a couple data points as input. Once we get hundreds and thousands, well, this is where we're not doing it by hand anymore. We're not doing it manually. We're not even able with historic data to write manual algorithms to figure this out. So that's where machine learning is going to come in. Let's pop back to the slides then and continue our discussion. Now, the thing that Excel did with that one piece of data actually is something called linear regression. But linear regression does generalize to more than one feature. Linear regression is actually really, really simple to understand. That's why it's the one we're going to dive into here right now. So linear regression basically is feature, like square footage, times some parameter. And this is actually how we're going to help flex the data as these parameters, plus other feature, bedrooms, times some other parameter. And that's going to give us our guess or our label. All right? Now remember, we're starting with historic data, but the idea is that later we're going to be able to feed in square footage and bedrooms in a situation where we do not know the price, so that we'll be able to get a pretty good guess. And by going through the historic data and trying to evaluate this and see if we come up with a price that is close to the one that did happen in real history, that's how we know if our algorithm's doing pretty good. Now, this linear regression algorithm is pretty simple, and it needs those parameters, or things that we'll call weights, right? So these weights help us, because if we look at my data here, notice that the square footage increases linearly with the price. But the bedroom count only slightly modifies the price. So we can't just blindly apply both of our features in the same way. This is where our weights come in. Our weights, or our parameters, when we actually write this out using math, like whether it be R or MATLAB or something like that, we'd actually, or for that matter, by hand mathematical notation, the convention is to use the theta symbol. So sometimes you'll actually hear it called theta, but you'll also hear it called parameters or weights to the algorithm. But the idea, in any case, is to say, okay, some of these features will matter more to the ultimate output. So what we end up with is our well-known algorithm that is like linear regression, right? So I've got my linear regression algorithm plus some parameters or weights, not plus in the mathematical sense, but in other words, I need both of these things. I need my well-known algorithm and I need my weights and parameters. This is going to give me some hypothesis. In other words, it's kind of a completed algorithm, right? That well-known linear regression doesn't by itself solve our problem until we give it a set of parameterization. Once we have that set of parameters, then we have this final algorithm, which is known as a hypothesis. And if it ends up being the selected real one that really does do a good job of predicting our data, will end up being called a model. Right now, it's just a hypothesis. In other words, we are going to run some data through it and run an experiment to see if it works. So that's why it's called a hypothesis. So with the hypothesis, we'll then run records through it one at a time. So this hypothesis we can think of as almost like a method, right? Or a function. And we'll give it a single record. Now, a single record is like a struct. So it includes all of the features of a single record. So in this case, this would include square footage and bedrooms for a single row, if you will. And then that will give us some result. And the result, again, as I mentioned earlier, we call a label, right? So we call that output, whether we're talking about the historic data or the predicted value, we call that the label. And in this case, our label is about the house price. So this is kind of a pseudo-mathematical notation almost here. As a C# developer, it might look something like this, right? We want to get the house price. We want to get the ultimate house price. So we're going to use the linear regression library function, right? So this is the well-known one. This isn't necessarily customized until we give it our weights. So we give it some set of weights, and we give it an individual record from our house data. So again, this might be a list of house data items and each one, I'm putting the 0 here just to say, it's a single record, and each one of this record is going to have the square footage, the bedrooms, maybe a lot of other things like the age of the roof and whether or not it has a city sewer coverage or, septic tank type thing. So it might have a lot of data in here, but it has all of that for one single house. And so now we can guess the price of that house. And so basically, these two things, the well-known algorithm plus the parameters, are our hypothesis. This is our single record, so our features, and this gives us our label when we actually run the algorithm. So taking our same concrete example from our Excel, if I have my record here, 1,000 square foot with one bedroom, that gave me an output of 50,000. So I run this through my linear regression algorithm with these weights. Now here I have to kind of confess something, which is that I said that they're weightings. In other words, one's more important than the other. The square feet are more important than the bedrooms. However, since they're on such a different scale, I actually have cheated here by making the bedrooms weight really a large number so that the math kind of works out. Technically, you can do this, but in a real world example, you'd actually really want to scale your features first. In other words, just kind of put them in the same order of magnitude. I'm skipping that step for the sake of simplicity. So once we have all this, here's how linear regression comes to a prediction. It takes my 1,000 square feet times my weight for feature 1, which happens to be square feet, plus, and then 1, and the weight. That should actually be 2,000. It looks like I have 20,000 there. So anyway, that should be 2,000 though, right? So that gives us a prediction here of 52,000. Now I mentioned already about the scaling, and we'll see that my prediction is not exactly correct, but it's in the correct ballpark. And actually, if I go back to my Excel document real quick, we'll actually see that was pretty consistent here, because even in the Excel document, the trend line ended up a little bit higher because some other data pulled it above. So my trend line, this would be my prediction, is not exactly correct. It's a little bit off. So, okay, we can see, given, this stuff, how I can run the linear regression algorithm and get that prediction. But where the heck do the weights come from? So I have these weights, and if I have the right weights, I get a pretty decent prediction, but where do the weights come from? Well, this is where the learning comes in machine learning. So we have to do something called training our model. And that basically means running through a lot of hypotheses and trying to find the one that works best. Now, this part is that first loop, or one of the loops that we talked about. And this first one is machine-based. This is the one where the algorithm takes care of it. This is also another part where kind of we get into redundancy, right? So we have some redundancy again here where we talk about looping and can make things a little bit hard to understand just because we keep repeating the same concepts over and over again. It can be hard to peel away the onion and figure out where one layer ends and the other begins. But let's take a look. So the way this learning process happens, and by the way, the redundancy that I'm talking about here is we started with a well-known algorithm, a statistical algorithm for linear regression. But linear regression expects weights, right? Now, in order to get the weights, I have to run a learning algorithm. So again, that redundancy and that overloading of concepts, right? So I have to run a learning algorithm to train the model to get the weight. So what this basically looks like is we, as the engineer involved, or when we have a data scientist involved, are going to basically select a starting weight. Just select some starting point, semi-random perhaps. We'll go through all of our historic data, potentially, millions of records. We're going to go through all of our historic data with our selected algorithm and the weight that we currently have, and we're going to run the predictions. For each of those records, we'll see how the prediction matched the label that we already have, right? So since it's historic data, we already know the house price. And then we'll adjust the weights automatically. Now, how the automatic weight adjustment takes place really depends on the learning algorithm involved and what kind of other parameters you use. So we're going to automatically adjust our weights, and then we'll once again check the prediction. We'll compare we'll adjust our weights and loop through all of our data again. So all of our millions of data of records again. And once again, check our predictions against the real world, and once again, adjust the weights. And we just keep checking and adjusting until things stop improving, until we can no longer tweak our weights towards, better results. So that is done, and in fact, what I'm describing here is a specific learning algorithm called gradient descent. Now, there are actually some learning algorithms that can actually do this without any loops. They actually, they use complex matrix mathematics and do crazy, math stuff to actually handle it without loops. But the idea is basically the same. They're trying to find the optimal set of weights, or the optimal theta, optimal parameters for, in our case, our square footage and our bedroom. So what are the optimal multipliers to make those give a nice prediction? So everything's starting to get pretty complicated at this point, even with the simple example of linear regression. So let's take a recap. We start with our historic data. We have that historic data where we know the answers. Then we take a guess at some optimal weights and kind of take a guess at the algorithm itself. We know that we want a algorithm that's for scaling data, so that gives us a starting point, but there are some options even within that. Then we train the algorithm. And that means actually running a learning algorithm that will find the optimal parameters for our, statistical algorithm, in this case, linear regression. So basically that just loops through all of our historic data, and it loops through all of our historic data for every single set of weights that it wants to try. And it keeps trying new weights until it finds the optimal set. And again, sometimes it can skip the actual looping process depending on our data, our algorithms, and some choices we make. But the idea remains the same. So at this point then, maybe we're thinking to ourselves, all right, great. We have our optimal weights. That's our optimal parameters. Our algorithm is just, some well-known out-of-the-box algorithm, so we must be done. Well, unfortunately, it's not quite that simple either, because the data that we input might not be perfect. Right now, I only have 2 columns. What if I want to add a lot more columns? What if I potentially in my historic data can find other relevant correlated data, like the age of the roof or whether it's a septic system? That's relevant. That's predictive. I should include that. What if some of my data doesn't actually have values because, maybe it was manual entry, so I've got a lot of nulls. So maybe I've tried some different techniques for populating those nulls. Maybe I used mean. So there's a lot of different ways we can clean up the missing values. Sometimes we may have outliers where somebody just typed 0. It's a numeric field. Again, it's, manual entry. Somebody just typed 0. We have to go through and try to figure out how to handle that data because it can very much confuse the machine learning algorithms. And quite frankly, sometimes we just have to manually kind of massage features like create ratios, might be square footage divided by number of bedrooms. That might be a more relevant mathematical representation. And if we're using something simple like linear regression, we actually do have to manually pick those features. You use something a little more elaborate like a neural network, and maybe you don't have to manually pick those features, but you may have to wait a much, much, much longer time. Literally could be, hours instead of milliseconds, depending on, the size and shape of your actual data. So neural networks, skip some of the steps of a person having to pick the data, but then the processing time involved is much larger. So all of this depends. Heck, even whether or not you choose linear regression or a neural network is a decision that you're going to have to keep trying. All these different things, you're going to have to keep trying. You're going to have to keep looking and seeing, how did it perform when I used neural network? How did it perform when I used linear regression? How did it perform when I removed the outlier data versus how did it perform when I included the outlier data? So this is the human looping process, and this is why things aren't necessarily always just so easy. So in the end, it's going to look something like this. First off, we start by splitting our data. That is, we're going to take this other piece of data here, maybe 20% of our data, we're just going to set it aside. And this is what we're going to train our model with over and over and over again. We're going to call this our validation set. And in some cases, you might even split it off 3 ways and have an ultimate test set, but we'll skip that discussion for now. So then at this point, you kind of do your data cleansing, feature selection, and in fact, you might actually do this, probably should do this before splitting your data. But you get your data and you're going to go through and make sure that all of your data is the way you want it. You've removed outliers, or you've included averages for missing data, or you've included some string where the user didn't enter a name. Whatever you want to do with your data cleansing process. And I'm sure as experienced engineers, most of you are very familiar with having to deal with data cleansing. Then we select our algorithm. Do we want a neural network, or do we want linear regression, or what do we want? And the initial set of parameters. Then we train the model. That is, let the training algorithm kind of find the optimal set of parameters for the given set of selections that we've made. Optimize what we've done. It can't fix the mistakes we've made, but it's going to optimize it within what we've done. And now we can evaluate. How did we do? Given how we selected things, what's the best that the machine learning could come up with? How close was that machine learning algorithm able to come to predicting house prices given our historic data, given our validation set here? So it trained our model using the 80% of records, and now we can go and look at using those 20% that we set aside and say, did that trained model actually predict accurately what the house price on these would be? And kind of regardless of how well it did, we still want to try other options. We still want to play around with other options to see if we can do even better. Now, maybe it did terribly. Maybe it did really well on our first try. Either way, we're going to want to keep playing and see if we can improve it slightly. Now, you can eventually get to a point where you're happy with the result and then be done. Or you may continue for years and years and years trying to completely, optimize that algorithm. Take facial recognition. Nobody's going to stop trying to improve facial recognition algorithms. Even though they're good enough now to do a pretty good job at a lot of our use cases, Nobody stopped working on them. Nobody stopped trying to go through those manual processes and loop through and validate their data and see if they can do even better. We still keep trying to improve this process. So it can be never ending. This actually brings up an interesting point about what Azure does for us. In the old days of machine learning, you could do all of this, but you'd end up with this statistical model that's, pretty accurate, but how do you now deploy this? It's like written in MATLAB or something. So you have to hand this off to a C++ developer who will then have to try to translate all of this using some statistical library into something that's deployable, that's production deployable. So that obviously had a pretty huge latency to it in order to get your production model working, in order to get your statistical model doing things in the real world. Well, with the new wave of how things work with like Azure Machine Learning Studio, you literally figure out what you want from your statistical model and hit the deploy button. And boom, it's just in the real world doing it for real. There's no need to have somebody take MATLAB code and translate it into C++ code or something like that. So another thing that's pretty cool about Azure Machine Learning Studio, and we're just about to get into it, no more teasing, is that it's kind of drag and drop in a lot of cases for a lot of what we're going to do, as we'll see. And the diagram looks not totally dissimilar to what we're doing here. So it works intuitively. We're going to drag and drop tools. I know kind of visual programming may not be the most exciting thing to a lot of developers for a good reason, but it actually works really, really well in this case. So it's time to do it. Let's actually get into Azure Machine Learning Studio and do some real work with some real data. All right, let's get Azure ML Studio open. Here we go. So here I'm just going to open up my workspace. Notice that is a free workspace, so that means that everyone is pretty much going to have the same access that I have here. Nothing special going on. Let's zoom in a little bit so everyone can see nicely, and we'll just get started. All right, so I have some experiments I've done before, but today we're going to be getting started on a brand new one. All right, so let's go see. I've already uploaded a data set, and that, of course, is pretty easy. Actually, we'll be using this class attendance data set right here. This is actual Xamarin University historic data. So this is how well our classes have been attended. So this is real data for a real business problem that I'd like to solve for my organization. This is actual Xamarin University attendance data. We can actually start to do some predictions on how well a class will be attended in the future. So let's go to experiments here. And I'm going to actually click new experiment in this case. Blank experiment. And you can see we're getting this kind of diagram where we can start just dragging and dropping tools. And the very first one I'm going to drop is my saved data set. So I'm going to come over here and, not samples, I want my data set. So that's the class attendance. Just drag it onto there. And now it clears that template out of the way and lets me start actually working with my actual diagram. And one of the interesting things is, as we're diagramming things, we can always come in here and hit visualize for every step of the way so we can see how our data is being transformed and how the calculations are going. And here actually is the data set that we're looking at. We've got 6,800 roughly rows, and these are the actual datas right here. So you can see the different instructors, the different classes, how many people registered, and what the attendance was, and of course the class time. Over here we can see different interesting things about the data, and we can actually see a histogram when we click on a single column. And I can see my instructor. We can see that Glenn has taught more classes than anyone, and and then a few of us are kind of tied in the middle there. Okay, so from here, now what I want to do is actually, I need to modify our data just a little bit. We do have a data cleaning step that we're going to have to take. In this case, it's because some of our input data, most notably the classes and the instructors, aren't really scalar values, right? They don't really have incremental values. So in order to feed those into my attendance algorithm, I'm going to actually need to make those categorical, or kind of like enumerations, really. So I'm going to find my edit metadata unit here. And then what I'll do is drag and drop. And now from here, I need to actually do some modification. So first of all, launch the column selector. And it is the course and the instructor that I want to modify metadata for. And then what I want to do, notice we could change the data type, or I can make categorical, or I can change some, whoops, we don't want to do that, unchange. We can change kind of some of the calculations about the data there. All right, so that's good now. Next up, I'm actually interested in doing my data split. So now I want to get rid of some of the data, set it aside so I can check my models with it later on. So come over here and do a split data. Actually, before I drag and drop this on, let's actually look at the metadata output now. Remember, I've mentioned that we can always continually look as we keep building up our graph. We can look at how our data is being modified and transformed. Now, notice it was grayed out. This is because I actually do have to run this here. So let's run this. It's going to actually take my data here and pump it through the one module that I've given it so far. Now I can come in here and visualize how my data has changed after running through that module. And nothing obvious visually, but now we can actually see that it's a categorical feature, right? And our unique values are right there. So nothing obvious, but so far, so good. We've actually made it this categorical feature that's going to make it apply to the algorithm correctly, because a string wouldn't have really worked very well for us, wouldn't have been able to actually provide much predictive value for us. All right, so we've done that. Now we'll take that split data as I mentioned. And now I'm going to drag the output of edit metadata into my split data here and highlight that. We'll come over here and say, all right, what split do I want? And I'm actually going to say the fraction of rows in the first output will be, say, 80% of them. All right, so I'm going to take 80% of those and use those to end up training my model, which is actually our next step. So now I'm going to come in here, and what model are we training? Well, I already told you that we're going to play with linear regression here first, right? So let's find my linear regression model. This is going to be then that pre-built, well-known algorithm, right? Now I'm going to move that over to the side here. And the reason for this is, as you guys will actually recall from our discussion, we need the well-known algorithm as well as the weights that we kind of have to calculate. By the way, we can actually mess around with how we calculate those weights over here, but this is fine for now. We need to actually calculate the weights, and we do that by having our machine learning algorithm train the model, right? Go through loops and just kind of zero in on the optimal weights, the weights that make the best predictions as far as the training algorithm is concerned. So now I will say, all right, I need a train. Actually, that gave too many results, so let's add train model. There we go. Train my model. Now, with my train my model unit here on screen, I can say, all right, my train is going to use linear regression. It's going to train using linear regression as the well-known model, the well-known algorithm. And it's going to use, of course, my data in order to process, in order to calculate the weights and eventually create a prediction. So I'm going to have to actually highlight train model here, and it's telling me that it needs some more information. I need to tell it which field I want to predict. I'm going to come in here and I'm going to say, all right, I actually want to predict, and I'm just going to include column name. I want to predict attended. Click OK. Notice that says label column. Remember, the thing we want to predict is called our label. Okay, so at this point, let's run it again. One moment. It's working through. All right, everything's done. It's training now. And now we can come in here and we can visualize. All right, so it's telling us some things about how it calculated. And notice we have here our feature and our weights. So it figured out the optimal weights. Notice when I categorized things, what happened? In order to categorize, in order to use our categorization to learn from, it actually has to take every single option from those, and it has to turn each one of those options into an independent Boolean column, binary column. So in other words, each record has to say, was it Rob Givens? Was it Jason DeBoever? True or false? So when you categorize data, each one of those becomes their own feature, which is kind of interesting. All right, so we've got that. So now let us take our trained model and use it on some fresh data, and that would be the rest of the data from here. Use it on some data that we didn't use to actually train the model and see how well it generalizes, how well that prediction is able to continue predicting new data. So let me grab the score model here, drag my now trained model. Remember that the trained model now includes the well-known algorithm plus all of our optimized weights, all the weights and parameterization, the theta, that is correct for the given features that we have in our data. And theoretically, this data from this 80% and the data from the 20% should follow the same rules. So all of that parameterization, the weightings, should actually be similar. And so we should get a pretty good score, see a pretty good trend when we do our score model. And so actually, in the interest, since it takes a few seconds to run every time I do it, let me also drag and drop our other unit here that we're going to use, and we'll look at the output of both. So I also want to do an evaluate model, and this is just going to give us some statistical information about how well our trained model did after it got scored against the test data here. So we'll just drag and drop that, and we'll look at both. There we go, it's scoring. All right, let's come in here. And now I'm going to once again visualize and see what we've got. So this is actually our test data that we're looking at right here. And our test data, notice, has another column, scored label. So this is actually the prediction that we've now made on what the attendance is going to be. And you can see the actual attendance here. So it used these 4 columns in order to predict this one. And then we can actually use the real value here to see how well did it do. So we can just kind of browse and see, all right, it said it guessed 2.5. We could make this integral, by the way, instead of having this be a double. So here it's a double. So 2.5. Whatever, it's good for demo purposes. Here it guessed 12.5. We can just see how the real world applied. Interesting things we can do with these visualizations here. Now we have the histogram here again, but I can also take that attended and compare to the scored label. And now we can see, all right, when the real world had 20, well, in general, we did a pretty good job. The cluster of scored labels was pretty close. When the real world had, here's the attended, had 40, again, the line, we would want a perfectly slanted line, right? Showing that 45 corresponds with 45, that 5 corresponds with 5, and it's pretty good. Obviously, it could get better. Now, how do we actually quantify could get better? Well, that actually is something we can look at in our evaluate here. So here I'm going to look at the output, the visualization of that evaluation. And this gives us some statistical values. The easiest thing to look at here is the mean absolute and root mean squared error. These are 2 things we want to minimize. Obviously, the mathematicians concern themselves with a lot of other metrics, and I won't get into those. A lot of the links, though, if we follow the links that I have for this course at the end of class, I'll give you those links. those classes, those much deeper materials, will get into really exactly how to judge the quality of your model. Right now here, though, we can see we have two numbers that we'd like to minimize. Whether or not this is good enough or bad enough depends on a lot of choices about your business, but they are numbers that the lower is better. So we have a predictive model now, just like that, and it took maybe, 5 or 10 minutes here, and we've got a predictive model where we're actually able to come in here and say, you know what, it didn't do too bad. It actually is saying, all right, I expect 2.5 people, and we got 2. I expect 11.5, and we got 9. It's not perfect, and it's real world data with real people doing real things, so it's never going to be perfect, but it's not bad. However, not bad is not necessarily perfect, so there are maybe things we can do besides. That's not the zoom. Let me get that zoomed. And this is where that human element to the looping comes in, right? So the reason this is called an experiment, because we're not done just because we threw something together. So there are other things we can do. One thing we can do, for instance, I'm going to actually disconnect linear regression. So we're going to start experimenting. We're going to play around a little bit here. So linear regression is one way we can try to predict scalar values, and it's the simplest. And we talked about really what the logic behind it was, how it works a little bit. Now there are much more complicated ones, one of which is a neural network. And you guys have probably heard a lot about neural networks. Neural networks are super cool. They are actually pretty super cool, but they are a lot more computationally expensive. In our case, we only have 6,000 records or something like that. It's going to be fine. It's not really going to hurt us at all, and it's going to give us better results, presumably. Now, what the neural network can do, and it gets pretty complicated, but it can kind of create do some of that feature engineering for us. That is, it can actually mix and match kind of ratios. It could take the attended ratio take the registered and attended ratios and kind of work those numbers together. It can square values and create just more complicated interactions of the known fields so that the mathematical algorithms can have a chance to find more interesting patterns. So let's let it do its thing, and you can see there's a lot more options here for it to actually go through, but we're leaving all of those alone at the moment, and we're going to rerun our test. Now, I'm actually going to keep this aside right now. Oh, I already lost my evaluate model. Changing it has made my... We'll actually go and see it anyway here shortly, but let's go ahead and run it with neural network regression. And again, just give it a few seconds to run. Remember, all of this is real time. Let me zoom in a little bit so everyone can see it doing its thing. Oh, that was zooming in a lot. Almost there. Giving us our evaluation. All right, we are there. So if we go and look at our scored model again, we can once again see some of the data that was predicted. So we can see, here predicted 2.6. It was actually 5. That's not a great one. This predicted 9. It got 9. That's a pretty good one. So various levels of accuracy here. Let's go and actually let's do our visualization on the output again there too. And actually take my scored label and my attended and just look at that trend line there, that scatter plot. Okay, so once again, looks pretty good. In fact, it might be a little tighter. It's hard to say. It's hard to eyeball and say if it's tighter, but it might just be. Now we can look and get some actual quantification on whether or not it's better. So now I have these two values. I have 1.80 and 2.50. All right, so try to remember those. 1.80, 2.50. Let me do a copy here just in case my memory's not so good. Grab those. And I'm going to go to run history now. And on run history, we can go through and find our last run through. This was with the, that was with the neural network. Let's go back and find our linear regression run through. There we go. There's our linear regression run through. And now we can compare that. Visualize that. Here it was 2.25 and 3.5. That's as opposed to 1.8 and 2.5. So we've clearly improved things by switching to neural network regression. So that's clearly an improvement. And this is part of the process that we go through in trying to create predictive models, is just tweaking things. Try different algorithms, try different parameters on those algorithms. Again, if we look at neural network, there's a lot of options, right? So we can, changing the number of hidden nodes, for instance, will often increase the result quality, but it will also greatly increase your CPU load. Another thing we could do is manually engineer some columns. Now, we can do that in a lot of different ways. We could do it with SQL. So with SQL, we could just select new data and then use, for instance, aggregate functions. We've actually got a SQL node where we could just select new features out, for instance, perhaps doing aggregations. But it does use SQLite syntax, not Transact SQL syntax, so bear in mind that. Other things we can do, and actually I'll do one of these. We can do Python or R language. So R is very, very common with statistics. We full-time developers maybe don't use it that much, but it's used very often for statistical models, and that's why it's included here. And then Python is also an option. No C# though, I'm afraid to say, no C# options. So we're going to use R. So I'll do the R. Oh, let's see, we have to find our R script here. Here it is. Execute R script. And I'm going to use this to actually do a little feature manipulation before we go into our split data here. And I'm going to add a whole new column where I'm kind of theorizing that if I look at our most recent data, that I will actually have a better predictive result. In other words, if I say, okay, given class XAM 330, for XAM 330, what's been the attendance over the last 30 days or 120 days? And again, I could just play with what parameters I was using there, whether I was using 30 days or 120 days. It's just kind of an experiment process. What gives me the best predictive results? So that's my theory. We don't know if it's true or not, but I want to create that calculation and add it to my data set. And I'd have pre-written the R script here because nobody wants to watch me try to figure out how to write an R script because I'm not an R expert in real time. So I did that ahead of time, so we can just copy and paste. Now, in our R script here, our mammal.map import port, this is basically to pull the data out of that node right there. And then, of course, 2 is to get it out of that node right there. And then we can also map output port to send data back out. And in the interim, we can do all sorts of interesting transformations. So I've also got here, my test script also has some if I'm running locally, then load it from my own file system. So here's the Azure syntax that we're using. And then here's my Azure output. In the meantime, what I've done is grouped and then run a transformation on the data. So I basically said, all right, grab the last 120 days worth of data for every given class. So I've grouped the classes, and then I am getting, for the last 120, the average of the ratio attended to registered. So I want that ratio for just the last 120 days worth of classes because, hey, we change, for instance, which classes are on the certification track. So that changes how popular classes are. So my theory here is that maybe the more recent data, the ratio of attended to registered for more recent data, is more relevant. We'll see if it's true or not. Then I'm going to actually do a join to join that grouped roll-up data, that aggregate data, back into so that every single XAM 330 shows that ratio as one of its columns. All right, so this should do it here. I'm going to hit save and rewire that column there. and then wire my output to my split data. And it's really that simple. Split data still works. It's still grabbing 80%. It's just grabbing 80% of a data set that has more records. Train model still works. It's still training to predict the attended. It's just using all of the input fields it gets as features. And so now it's getting one additional input field. Super. Everything is ready to go. Let's hit run. There's a very good chance it'll take a few seconds or up to a minute to run that R script the first time. It's got to load that into memory and parse it and all that good stuff. There is an option to actually run it on Microsoft OpenR if you highlight that and go into the R version. And OpenR can theoretically sometimes run a little bit faster. I didn't think to do that before hitting run this time, but no, pretty much went zoom zoom anyway, so no worries. And now we wait for the evaluate. All right, so let's actually check out a few things. First of all, I want to look at my execute R script output here. And so now we can see that I have this recent attended ratio, and it doesn't match the ratio exactly of this particular row. This ratio is actually for all XAM 330s over the last 120 days, the average ratio. So it's theorizing that will help predict that this should be whatever it should be. And so, of course, we're going to go down and look at our scored model, check out our visualization, check out our scored labels now. And here, same 1.9, we got 2. This one's predicted 4. We actually had 1. Not great. So let's look at the trend lines here. My attended compared to scored label. And it's still roughly aligned, although it doesn't necessarily look like it's much tighter than before. So maybe my theory didn't hold. Let's go look at the numbers. When I visualize here, it is modestly better. Very, very tiny bit better, right? Very, very tiny bit better. We had 1.80 and 250, so I have 1.78 and 2. So didn't make much of a difference, did it? So now we know that. Maybe we try playing with some other parameters, some other interesting things, and seeing if we can engineer other features, other ratios, other things that might make a bigger difference. Since neural networks already engineer a lot of these features kind of for us behind the scenes and create a lot of interesting options behind the scenes, maybe I didn't give it any new data. It's hard to say. Maybe that would have had a bigger effect with linear regression, or maybe not. But that's why we experiment, right? It's not nearly as deterministic as programmers tend to like. Even though this is all programming and we're writing software, a lot of times developers seem to like deterministic programs. And when we're running our programs against all of this data, the logic definitely becomes fuzzy. So maybe it would never help. Maybe my whole theory is completely wrong. That's why we run the experiments. That's why we check. All right, so at this point, I'm going to leave that in place, even though it didn't make much of a difference. And now we want to publish this because we want to be able to, for instance, have the Xamarin University mobile app be able to, whenever some group of people is registered, predict the attendance. Say, all right, there's 25 people attended or registered. We expect there to be 18 actually show up. We want to be able to predict that for every single class from here on out. And so we're going to have the Xamarin University mobile app plug into a web service that we create. So here I hit create predictive web service. So this is actually going to deploy it in the real world and give us the ability to call a web service, a REST web service, instantly and run through the logic that we just created. Now, notice here, I'm going to move this aside. We kind of have almost a dotted line sort of connection to our old training data. This just kind of shows that our model was trained using this data and that it applies the schema that we get from this data. But we're going to be working now on the input we get from our web service input. By default, it's going to be going through the same edit metadata, the same R script stuff. It moved things around a little bit to create our web service flow here. But it tried to make a best guess at what we wanted based on what we did in our training experiment. So training experiment over here, and the predictive experiment is basically our web service over here. Now we can actually modify things. If our web service, for instance, maybe our web service has no need to take in the attended, right? Because attended is historical. The idea is that we never actually know attended when we're calling this web service. So it's not something that we would probably actually take in our web service. So we can actually go and change our columns, change everything here separately from what we did in our training experiment. But by default, it's pretty much the same. So the experiment created on, this actually becomes our trained model. This actually is our trained model right here. And in fact, it will show up over here in our trained models. If I find the right one here, there we go. Here's our trained model right there. So this means this is the algorithm plus the parameterizations that were learned from our data. All right, let's go back to our experiment here. And so it's going to go through, use that model, and then take the input data that goes through this funnel, the trained data, and give us our prediction right there. And then that, of course, gets changed to the web service output. All right, so we have it created. Now let's deploy it. Oh, we have to actually run it first. So we can see the runtime up there, and it should not take any longer than our training did. All right, ready to go. Now deploy. All right, now right off the bat, we could start testing. So here's the API key. If I look at the request response, this means basically one input, one output, or I can do batch execution as well. Notice we can even download an Excel workbook that has a plugin ready for us to input our own data and call our own web service, so that, especially for batch execution, that's extremely convenient. Hit the test. All right, my course. Now, of course, I have very strict data that this needs to conform to, so let me copy and paste some of that, otherwise I might get it wrong. So we'll use Jason's name. That guy's pretty cool. And we'll say that the course is going to be XAM 300. Now these have to match exactly because they're categorical. Remember, they're like enumerations, and it's just the test form isn't rich enough to actually do that for us. So registered, let's say we have 50 people registered. Attended, I don't actually care about because, again, we didn't edit it out of the inputs, but it's not strictly relevant to us. And we'll say that the class time is 2017-07-01. All right, let's give it our run. You can see that it's running down here, and there we see experiment returned, blah, 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 and it predicted 24.9. There's our prediction right there, 24.9, based on 50 registered for XAM 300. So our prediction worked, called the web service correctly. And so if we want this to actually be called from, say, our mobile application, we're going to obviously need the endpoint. So we'll just click on request response. And this is actually going to send us to a little landing page that tells us the endpoint and gives us some instructions on exactly how to send the information, along with a sample. A sample with fake values, but a sample nonetheless. That's it for our Azure Machine Learning Studio demo. Let's get back to the slide deck, shall we? And it's actually almost time to close things out on our question and answer period. But before I get there, first let's remind you once again about Xamarin University. Of course, we use sample data from Xamarin University today. That's where I work. I give live classes each and every day along with a bunch of other awesome instructors. We also do one-on-one. We also have self-guided learning if you don't necessarily want to wait to schedule a live class. We've got that, as well, of course, as our mobile developer certifications. All of this is now available on a monthly basis. No longer do we require an annual subscription, so this makes it obviously accessible for a lot more people. Please check that out. All right, our resources, the things that can help us dive even deeper on some of the stuff that we've been talking about in this webinar series. Of course, you'll want Visual Studio and Xamarin. Download those there. And of course, all of the machine learning stuff that I demoed today was on Azure Machine Learning Studio. To learn even more, we've got some more introductory content similar to what we've done today at those links. And then when you want to see some other ways people have solved problems using Azure Machine Learning Studio, you can actually check out our gallery of tutorials and samples that are available. There's actually a ton of information there that solve a lot more complicated problems than what we did today. So a lot to learn just by seeing what other people have done. Now, if you actually want to dive deeper into actually longer classes, the Coursera machine learning course isn't Azure ML specific. However, it is very deep and very good in teaching you how machine learning works. And that's actually an 11-week course. The Microsoft Virtual Academy course actually is Azure Machine Learning specific, and it is a several-week course as well. So also very, very useful information. Really help you start to understand the inner workings of machine learning stuff by taking those two courses. Then, of course, once again, Xamarin University and the Xamarin University webinars. Check those out as well. We've got other interesting webinars. The other ones actually hew a lot more towards the mobile development area, so that's also super interesting. Mobile games, things like that. You can see how to develop those in Xamarin with those webinars. All right, guys, thank you ever so much for hanging with me for this discussion that has run a little bit long. It's been actually really great to present this material to you guys. And now it's time for your questions. You can go ahead and ask those questions in the chat window, and me and some other people will be there to hang out and answer them. Thanks a lot, guys. Bye for now.